Hello everybody and welcome to the NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 19 and we will be looking again to the various characteristics of semiconductor devices. We will start with room temperature and then we will go down to temperature. So, what we will be looking into, we will be having a look into the various electrical characteristics of the device or the material. So, the outline of the talk is we will first have a look at how do we define the Fermi level position at room temperature. We will also look into what is defined as conductivity and then we will have a look at what is defined as mobility of the particle of the free charge carriers, which is electrons and holes at 300 Kelvin. We will then subsequently have a look into study the variations of resistivity of the impurity concentration, electron hole mobility at 300 Kelvin, which is the same as the third bullet, and then we will finally end up with degenerate and non-degenerate semiconductors. Now, the motivation for this lecture is primarily to give you an idea about the behavior in terms of carrier and the material with varying temperature. That is the whole idea, so that you can appreciate how does, from the first principles of physics, how does the variations in various other characteristics of the parameters change with the variation in temperature. We have already discussed Fermi level with you. So, I told you that Fermi level was basically a level where the probability of occupancy is half. Intrinsic Fermi level is exactly at 0 Kelvin, is exactly in the middle of conduction band and valence band. And as you increase the doping and the donor level, if you are doing with an n-type semiconductor, starts moving towards the conduction band, and if you are doping with p-type material, it starts moving towards the valence band. That was the basic sort of initial understanding of the position of the doping concentration and the Fermi level. Now, what we have shown here is basically the intrinsic Fermi level, which is EFI, as a function of the doping concentration, right. So, when your doping concentration, and ND is the donor doping concentration and Na is the acceptor ion doping concentration. So, let us go for the dopant species, which is basically the dopant one, that above this dotted dashed line. And it has been seen that if you make your dopant concentration almost equal to that of the intrinsic carrier concentration, the blue line will converge with the dotted line here, dashed line here. And as the number of dopant ion becomes larger and larger, the Fermi level actually starts to shoot up or moves near the conduction band edge. This is my conduction band edge, this one, and this is my valence band edge here. So, it starts moving towards the conduction band edge, and this is sort of an interesting phenomena, and it comes from the first principles that as the temperatures, so this is fixed at 300 Kelvin, as the dopant ion goes on increasing, more and more species of valence of electrons are contributed to the conduction band. And since Fermi level is the probability of finding the electron, obviously it moves to the up. Similarly, if the acceptor ion concentration, it goes down, right. And interestingly, if you look at the separation between the intrinsic Fermi level and the Fermi level for n type and the separation here, they are almost the same, which means that if the number of dopant species which you add is exactly equal to the number of acceptor species you add, then the shift in the Fermi level will be exactly the same, but in the opposite direction of the intrinsic Fermi level. So, if this is, let us suppose this delta E is moving by 0.1 eV, then this will be also approximately delta E will be approximately 0.1 eV. This is what I wanted to ascertain to you as you move ahead. So, for an n-type semiconductor, the Fermi level will be moving more towards the conduction band edge, and for a p-type semiconductor, it will be moving towards the valence band edge, and the separation will be almost the same. The second thing to point out is at 300 Kelvin, if you make your dopant species very close to intrinsic, what is the value of intrinsic? Intrinsic is 10 to the power 10 per centimeter cube. At this particular point, you will have your EF will be almost equals to EFI, the intrinsic Fermi level, correct? And this is at 300 Kelvin which we are talking about. Let us take up a numerical approach to understand the shift in the position with respect to dopant species. Now, this is for the density of state actually. Now, the question is, you need to calculate the position of the intrinsic Fermi level with respect to the center of the band gap. The center of the band gap, if you see, is this is my mid gap. This is the center of the band gap. EFI is my intrinsic Fermi level. This intrinsic Fermi level shifts. So, what you are told to do is you are told to find out the difference between EFI and E mid gap, which is this statement, right, EFI minus E mid gap, and how is it related. So, typically we take the density of state effective carrier mass of electron to be this much and this to be this much. I will explain to you what this effective carrier masses of silicon are. So, you see, if the electron would have been moving in free space, right, which is not under the influence of any external biases or forces, push as well as pull, we define its mass to be as the rest mass, right. So, the rest mass is defined as when the carrier is moving without any effective potential or within a zero potential well. Now, if it is moving in a let us say an array of large number of silicon atoms, then its effective mass changes and it becomes a factor of the rest mass, a certain factor of rest mass, and that is given by this. If you look at Mn star is basically the effective carrier mass, and it is 1.08 times the rest mass, and Mp star is basically my whole effective mass, and it is 0.56 times the rest mass, right. And this Mp star and Mn star and Mp star are known as effective masses, and they are a strong function of the Ek diagram, which you already know. More steeper is the Ek diagram, higher will be the value. So, if you look at the value of the effective mass, it is given by h cut square by d2E dk2. So, if you plot E versus K diagram, more steeper it is, right, more will be the value of d2 at dk2 and low will be the value of M star. So, typically we look at the Ek diagram and from there predict the value of the effective carrier masses in silicon, right, and that comes out to be 0.8. Now, if you look at this formula here, which is EFI minus E mid gap, and it is given as 3 by 4 kT natural log Mp star by Mn star, right, and if you place the value of Mp star Mn star, you just get the value of EFI minus E mid gap to be this much, which is approximately minus 12.8 milli electron volts. What does it mean? It effectively means that once you know what is the value of the effective density of states, you can predict the value of it. Now, quite interestingly, if your Mp star is larger as compared to Mn star, right, you will have a positive value of EFI minus E mid gap, and if Mp star is lower than Mn star, you will get a negative value, and that is what you are seeing here, which means that EFI is smaller as compared to E mid gap, which means that it is going down in terms of the carrier concentration. Now, let us come to the next sort of parameter, which is very important when you work with cryogenics as well as in room temperature, and that is defined as conductivity. The unit of the conductivity is given as ohms centimeter or ohms meter, and is basically a function of electron and hole concentration. Now, if you look at the electron drift current density, it is given by this quantity here. Drift is basically the movement of the charge carriers and the influence of the electric field. Now, if you try to find out this, it will be comprising of two parts. One is that of electrons, right, another is that of holes here, right. One is that of electrons and another is that of holes here. The electrons will be primarily responsible for movement of the charge carriers in one direction, the holes will be in the opposite direction. The conventional current will be the same for both the cases, and therefore, you add the two and you get what? You get E into mu n into n. Mu n is basically the mobility of the charge carriers. This is Q, charge value 1.6 10 to the power 19. N is the number of free electrons available per unit volume, and P is the number of holes available, E is the electric field. This quantity is referred to as sigma, and this is known as conductivity. So, basically my drift is equal to conductivity multiplied by electric field, correct. So, what you get as conductivity is basically J by E, this is conductivity, right. If the conductivity is high, it effectively means that I will be able to generate the same amount of drift carrier density or drift current density for the same value, I will able to generate a higher value of drift current density for the same value of the electric field present, right. So, that is the reason it is given by J by E equals to sigma here. Sigma is basically the conductivity of the charge carriers, and the conductivity function of electron and hole concentration and mobility. So, higher the concentration, obviously higher is the conductivity, higher is the mobility, higher will be the conductivity. Plays a very major role because at cryogenics the mobility and the carrier concentration both changes drastically, and therefore the conductivity also changes drastically at very low temperature. Now, the reciprocal of the conductivity is known as resistivity, and that is shown here. So, resistivity is 1 by sigma 1 by q times mu n times c n times p. For all practical purposes, so let us suppose this is at T equals to 300 Kelvin, right, it is already given to you. Now, I am assuming that at T equals to 300 Kelvin, all these parameters q, mu n, n, mu p, p all are constants, they do not vary with temperature, right, because you are anyway keeping the temperature almost constant. In that case, your rho, which is the resistivity, and sigma, these are all constant, and they only depend upon the values, the parameters which I have already defined to you, correct. So, I have already defined to you the parameters here, which is rho and sigma. Now, if I vary the temperature upwards or downwards, these values mu n, n, mu p and p, they will vary, and therefore, rho starts to become a function of temperature, sigma also starts to become a function of temperature. So, just keep this in mind at this stage, we will go into deep down into it as we move ahead. At this stage, please keep in mind that at fixed temperature it is fixed, but as temperature varies, it also varies in a fixed manner. Now, if you plot resistivity with respect to impurity concentration, and why this chart is important, or well, this graph is important, is because it has been seen that as you reduce the dimension of the device drastically, you also tend to reduce the impurity concentration, right. This is basically following a scaling law. Now, which means that if for a lower node device or a lower node technology, my impurity concentration should be as low as possible, right. Now, if you look at this figure here, on the x axis it is impurity concentration per centimeter cube, and on the y axis it is resistivity measured in ohms centimeter. Then as the impurity concentration goes on increasing, the resistivity actually starts to fall down, which is very, from first principles, nothing very difficult to ascertain, because as you are increasing the impurity concentration, more and more, let us suppose donor impurities are being inserted, more is the value of n, and lower is the value of your resistivity, and that comes from this place. So, please look, this is basically a log scale, right. This is basically a log scale which you are seeing. This is actually the scale which you see here, log scale, both are the log scale which you see here. This is an order decrement which is happening in all these cases. So, this is basically a log scale, and therefore, if you look at n type material, which is basically a phosphorus here, right, and I have a p type material which is boron here, in both the cases, as the impurity concentration goes on increasing, I tend to decrease the resistivity, which means the device becomes much more faster at higher values. And you see one more thing, that for the same impurity concentration, both n type and p type, if you go, you will see that the resistivity of p type is slightly larger as compared to n type, and that is primarily because electrons typically have larger mobility as compared to holes. But as you move towards higher impurity concentration, the difference actually starts to reduce, you see, and it almost vanishes as 10 to the power 21. So, when your impurity concentration is 10 to the power 21 per centimeter cube, you end up having almost nil difference between the n type phosphorus and p type donor resistivity, right. Okay. So, let us take up a numerical approach to do that. So, we are told to design a semiconductor resistor, right, with a specific resistance and to handle a particular current density. So, what is given, a silicon semiconductor at T equals to 300 Kelvin is initially doped with the donors at a concentration of itna. So, what you do, initially you have a silicon slab, you dope with donor concentration 5 into 10 to the power 15 per centimeter cube. After that, you start adding acceptor to form a compensated p type material. I will explain to you what does this mean. The requirement from the designer is, from the user, is to have a resistance of 10 kilo ohm, which can handle a current density of 50 amperes per centimeter square when you apply a 5 volt initial supply. Now, understand the point that what is the compensated will come to it later on, but just for your information sake. So, we initially did a doping of 5 into 10 to the power 15 per centimeter cube. If I assume that 100% ionization has taken place, there will be as many number of electrons available to you. Now, what I do, I start doing a p type doping. So, when I do a p type doping, the hole gets added on, and let us suppose you have certain amount of holes. These holes will recombine with electrons, and the rest of the excess holes will actually generate a p type semiconductor. The idea is to have a resistance of 10 kilo ohm p type semiconductor which can handle the current density of 50 amperes per centimeter square at 5 volt. Now, if I apply 5 volt to 10 kilo ohm, I will get a current of 0.5 milliampere, very straightforward. If the current density which I am planning is to have 50 amperes per centimeter square, I know the cross sectional area can be given as, so you know J equals to I by A, because current density is current by area. So, if I want to find out area, it will be current by J. So, current by J, this is my current which is 0.5 milliampere. I know my J is limited by the user as 50 and therefore, which is less than 10 to the power minus 5 centimeter square. If I have anything less than this area, my J will shoot up, current density will shoot up, right. Anything less than that, this current density will be lower than that. If we assume that my electric field is set at about 100 volts per centimeter, then the length of the resistor will be voltage by electric field, which is 5 by 100, and that is 5 into 10 to the power minus 2 centimeter, because electric field is what? So, voltage by, so if you have a slab of silicon here and if you apply a plus 5 volt supply here, right, and this length you need to find out, right, and we already know what is the electric field present here. I can just divide the voltage by electric field and you get the length to be equals to this much. Now, the conductivity of a semiconductor, if you remember rho, resistivity is A by L. So, conductivity will be 1 upon resistivity, then therefore, this will be L by R into A. We already know the value of L to be this much, R is already known to you, area we just now found out, and we found out sigma to be 0.05 in this case. Now, the conductivity of a compensated p type semiconductor is given by this expression here, right. Why it is compensated? Because you initially did with dopant with donor species and then you added up acceptor. So, the effective number of holes will be nothing but the subtraction of Na minus Nd, right. Na Nd is given to you and you can find from here, from there, that the value of sigma will be equals to 0.492, right. And what we require is approximately 0.5 sigma is required in this case. We can take the electron mobility and hole mobility from standard values, and from there I can get the value of the output sigma to be equals to 0.492, which is approximately equals to 0.5, right. This is a general way of solving a problem with trying to find out sigma value in an effective manner. Let us come to electron and hole mobilities at 300 Kelvin, right, and that is again an important parameters, because if you remember when I was conducting or trying to find out sigma or rho, their mobility term was also coming. So, you should know as a designer to see where the electron and hole mobilities will vary at 300 Kelvin. So, if you take the impurity concentration here and you vary the mobility, as the impurity concentration goes on increasing, you see the mobility drops down, and it is a log scale. So, it basically drops down very fast. Now, the idea here is why it drops down is very simple, because as you go on increasing more and more impurities, right, you end up having more and more number of scattering centers, right. And it is something like this: if you have an empty room and one person is told to cross the room, he can easily cross the room, but you go on adding people inside that room, there will be a chance that he will tend to strike that person more often than not, and therefore, there will be a higher probability of scattering, which means that his mobility will go down. Exactly same thing happens in this case. As you enter more and more number of impurity concentration into the silicon, you end up having more scattering centers, and as a result the mobility will fall down. However, interesting phenomena is that the mobility remains almost constant of impurity concentration somewhere till 10 to the power 15 to 16. This region is where it remains constant, and then there is a drastic fall which happens here. So, it is visible to us, the decrement is very large for the impurity concentrations when it goes beyond 10 to the power 16, 10 to the power 17, and the decrement is much faster as you move towards 10 to the power 18 and 19, right. Obviously, as you can see here, the mobility of electrons are much larger as compared to mobility of holes, you see. So, mobility of electrons are larger as compared to mobility of holes, and this is because effective mass of electron is smaller. Since it is smaller, it can accelerate faster, and therefore, the mobility is larger in such a scenario. So, that is the reason it is higher in this case. Let us now come to degenerate semiconductor, a word which I have used in the earlier numerical problem which I showcased to you. Now, it is very simple. What is written here we will discuss, but let us first of all understand what degenerate is all about. So, let us suppose I have an intrinsic semiconductor, right. Intrinsic semiconductor primarily means that you do not have any dopant species. Now, I add donor dopant species and I go on adding therefore larger and larger number of electrons into the system, right. and therefore you have a bunch of electrons available. Now what I do a reverse doping, and I do p-type dopant species or acceptor ion dopant species, and then what it will happen is that it will tend to make the electrons, the free electrons will combine with holes, and if I would have doped with, let us suppose, extra 100 electrons, and then I put, let us say, 90 acceptor ions, then you will have 90 holes available. The effective number of electrons now will be 10 rather than 100. This is known as degenerate semiconductor, right. So, this is the methodology of formation of a degenerate semiconductor. Another concept of degenerate semiconductor in another sense is what is written here. There are two ways of looking at it. One is when you if ND is exactly equals to NA, you again come back to intrinsic. Now let us read what is written here. As impurity concentration increases, right, the distance between the impurity atoms will reduce. All of you are aware of this point, right, and therefore the donor atom electrons will interact with themselves. When they interact with themselves, this splits the donor energy level into a band, right. This interaction of two electrons or multiple electrons, say there are 100 electrons, all will split and the band formation will take place. Exactly, it happens in a forbidden energy gap. So, these are the band formation which takes place here. Now, if you further increase in the donor concentration, and it might happen that if you go on doping with very large number of dopant species, the Fermi level can actually go inside the conduction band, which means that even at 300 Kelvin without any external bias, you still have large number of free charge carriers available. So, it almost behaves like a metal, right. So, when I create a degenerate n-type semiconductor, the Fermi level lies within the conduction band, you see. So, what I do, the initially intrinsic Fermi level was here, I go on adding more and more donor species, this starts to move the top. It further moves to the top, goes inside the conduction band, sits somewhere in the conduction band. So, if you remember, I told you that Fermi level is the position from where you can find the number of charge carriers. So, all the levels between the Fermi level and conduction band will be fully filled up, right, and that is what I have written. These are filled states which are available to us, right. These are filled states. Filled states means almost behaving like a metal ion, right. So, semiconductor can sometimes behave as a metal when you define it to be as a degenerate semiconductor, right. As acceptor doping concentration, so it's what the previous was a donor, this is acceptor. This is basically a degenerate p-type semiconductor when the acceptor ion concentration becomes much larger and the Fermi level actually goes below the valence band. So, you now have full empty states available here, holes are available here, correct. This is a p-type degenerate semiconductor, and if you go to this is n-type degenerate semiconductor. This is not a non-degenerate semiconductor, right. So, these are the two differences. We might encounter this as we go to certain low temperature, because the Fermi level itself shows a movement with respect to the temperature at these low temperature. Let me recapitulate. What we did here was we actually looked into the variation of mobility and conductivity and resistivity as a function of impurity concentration at a fixed temperature. We also understood the definition of degenerate semiconductor with respect to dopant species for both n-type and p-type, right. And this will be the starting idea of the freeze out and incomplete ionization, which we will take up in the next class. With this, let me thank you for your patient hearing. I will meet next time.